All right, I think we are up and running. Welcome to the summer semester. I see, about 75 students are enrolled in this class, and it's good uh, because I see a lot of names that I've already seen before, so I know most of you guys. For those of you who are taking their first class with me, my name is Mahmood Hamid. I'm going to be your instructor for this class. This class is offered in the hybrid mode, so we are going to be online and in person at the same time. For the first class, we are all online, just because your COVID results have not come yet. But from Thursday, May 27th onwards, I'm going to be in the classroom. Low 4050 has been assigned to us. So for students who are on campus, I would invite you guys to come to the classroom in low 4050. For those of you who are remote, I'm going to be expecting you guys to stay connected with the lecture using this same Webex meetings. Today is Monday, May 24th. So my goal for today is to talk about the overview for this class. We'll go through some introductions. I'll introduce you guys to the teaching staff, talk about how this class is set up, what are the things that you will submit throughout the semester, exam dates, the grading criteria, and so on. So that's my goal, and then we can start talking about signals. So I'll go through some introduction. We'll do some signal classification. We'll start there. All right. So course information. My name is Mahmood Hamid. My email address is listed over here. These slides, by the way, are available on Piazza. So slides are on Piazza, and all of you should be added over there. If you are not, let me know after the class so that I can add you to Piazza, because that's going to be our one-stop shop for all the course-related material. So everything that needs to be uploaded, I'll upload it over there. Homework solutions, lecture slides, links to the videos, because these are recorded, back exams, and so on. Let's see. Our meeting time is Monday, Thursday, 10:30 to 12:05 p.m. It's going to be via Webex meetings, but we are also going to be in person. I've already sent you guys information about that. It is a pinned post on Piazza. So if you are logging into Webex meetings, not using an app, if it's an app, then you should see it in your schedule anyway. But if you're not using an app, then you can click on the link in Piazza and join. I think Webex also sends a 15-minute reminder email, or maybe a 10-minute reminder email, so you can use that email as well. My office hours are going to be hosted on Webex meetings. They are going to be on Wednesdays 2 to 4 p.m. Eastern Time. On certain Wednesdays, I may move them a little bit, but I'll let you know about that in advance. But in general, I'll be hosting office hours on Webex meetings every Wednesday from 2 to 4 p.m. Eastern. My Webex personal room link is over here as well. Now we have 3 members on the teaching staff. 2 of them are graduate TAs, and we have Kiwi Ma as our undergraduate student assistant. Their email addresses have been listed over here, and I would encourage you guys to interact with the teaching staff members using Webex Teams. So there are already Webex Teams spaces set up within our class where they will be hosting office hours. Ian asks a question, will you be in your office as well? No, I will not be in my office, Ian. Just because there is no way for me to regulate the number of people in my office. So that's the reason why I'm hosting office hours on Webex meetings. because I have quite a few students, about 120 students in the first half of summer, which will increase to about 190 students in the second half. So, you know, unfortunately, I can't open up in-person office hours. Okay, having said that, let me see if the TAs are online so that they can introduce themselves and talk a little bit about their research and anything else they want to say. Meng Zhang is um our first TA. He is going to be holding office hours on Mondays 8 to 10 p.m. There is a Webex Teams space created within our class. You would have to join this Webex Teams space first in order to see all the communication that goes on over there. Is Meng online? Oh, go ahead, Meng. Introduce yourself, and if you want to say anything to the students, that'll be good. Excellent. Thank you, Meng. Next, we move on to Nawaz Chaudhary, who is also a graduate TA. He is going to be holding office hours every Thursday from 8 to 10 p.m. Eastern. And again, there is a WebEx team space that is created for him within our class. So you would have to join it first, and then you can monitor all the conversation that goes on over there. Nawaz, are you online? Oh, go ahead. Yep. Thank you, Nawaz. We also have an undergraduate student assistant, Kiwi Ma, who is going to be holding help sessions on Mondays and Thursdays from 10 p.m. to 12 midnight. Again, there's a WebEx team space created for him. Kiwi, are you online? Go ahead, introduce yourself. Thank you, Kiwi. Now, the Meng, Nawaz, and Kiwi, you guys are welcome to stay here, or if you have some other things to take care of, you guys can leave the class as well. It's totally up to you. Now, I suppose everybody over here is familiar with Webex Teams. It's actually a very convenient, fast way to communicate with me as well as the teaching staff members, or even between yourself. So let me just show you how the interface looks like. And this is particularly easy if you have a application installed on your smartphone or your laptop. So I have it installed on my iPad here. So if I these are all my messages. If I go into Teams, then I can see all my teams, right? So if I click on ECSE 2410 signals for summer 2021, on the left you see all these spaces that are already created, right? So you should be able to see these spaces. One is general. All of you are added to that general space. If you aren't, let me know after the class and I will add you to that space. But underneath that, there are 4 other spaces. There is one for Meng, there is one for Nawaz, there is one for Kiwi, and then there is another space for recitations. I'll talk more about recitations in a minute, but there are those 4 spaces created within our class. And for you to be able to interact, join, talk about things, you would have to sort of go there, click on that space, join it first, and then you can be part of the communication over there. Right? So go to our class team, then join the space, and then join the conversation. Questions about, where the help sessions are going to be hosted? Okay, so it looks like you guys have a good handle on Webex Teams. Webex Teams is actually, my preferred way of communication as well. So nowadays, email has become slower and it's much faster to get a response on Webex Teams. You guys, for faster Q&A, try to use Webex Teams. I will be using Piazza to sort of push through big announcements, but for smaller announcements, I will be using Webex Teams Space. So there are smartphone applications for Webex Teams, Webex Meetings, Piazza. So I would encourage you guys to install them on your laptop or maybe even your smartphone, so that you can get all the updated communication. All right, let's go back here. Okay, so when you look at the TA office hours, you might get a hint of why they are set up the way they are set up, right? 8 to 10, 8 to 10, and then 10 to 12. So on Mondays, you have an option from 8 to midnight. On Thursdays, you have an option from 8 to midnight. So 4 hours each, which essentially means or indicates that your homeworks are going to be, is the screen? Are you zoomed in, Ian? Okay. Well, does this help a bit? Yeah, make the window bigger. Okay. All right. So homework, which is our regular thing that we will work on, homework will be due Monday and Thursday, which is why the help sessions are set up in the evening for that. Now the way I'm going to be posting homeworks is I will post a homework, I will be posting homework every class, but homework will be due in 1 week, right? So the homework that is assigned right now is homework 1. It will be due the following week. So the following Monday is actually a holiday. So we will not have class on Monday. Instead, we will have class on Wednesday of next week. So that's when homework 1 is going to be due. And then Thursday, May 27th, we are going to have homework 2 assigned, which will be due Thursday of the following week, right? So that's how the homeworks are going to be set up. And homeworks are sort of the most important thing to do in this class, because there's a lot of math, like Noah's pointed out. It's a math intensive class, so the more problems you practice, the better it is. Now, I'm also organizing recitations. These are problem solving sessions that are aimed at reinforcing and summarizing the weekly learning. So whatever lectures you have in a week, they will be summarized, and there will be some problems that the TAs will solve every Saturday from 3 to 5 p.m. Eastern. And I showed you the Webex Teams space where they will be hosted. Now, these will be recorded if you want to watch it later. These are optional attendance. You don't have to attend it. However, for a TA to hold office hours, there should be some number of students so that they can have that session. If sort of nobody joins, then there's no point having that session, which also means that it will not be recorded. So, that's as far as the optional recitation sessions are concerned. The TAs are going to alternate. Meng is going to start us off for the first recitation session conducted on May 29th. So that's the Saturday that's coming up. The location for this is the Webex Teams space within our class that I just showed you guys. Questions about recitation? The way the recitations are generally going to be run is, for the first hour, say 3 to 4 p.m., the TAs are going to solve some problems. And then from 4 to 5, maybe it will be open Q&A, right? So if you have any questions, you can ask them from 4 to 5. Okay, let's move on here to the recommended textbooks. See, I've not made the textbooks for signals and systems required. These are recommended. The primary textbook is sort of the Bible for signals and systems, really. The author is Oppenheim, Wilsky, and Nawab. The primary author is Oppenheim, who is sort of a pioneer in this field of signals and systems. I don't know if he's still teaching signals and systems at MIT, but he has taught it for many, many years. So his Signals and Systems book, the second edition for that, is going to be our primary textbook for this class. Again, it's optional, but it is a very good addition to the books that you would own. It doesn't matter if you have a hard copy of it or a digital copy of it, but that is a recommended textbook. There are other supplemental texts. There is Shom's outline for signals and systems, the second edition. It has many solved problems. So for practicing problems, it is an excellent resource. And if you are able to find an online version for this text, it will be good to have. There are other resources as well, but I'm not going to talk about that. The primary textbook, the Oppenheim textbook, and the Shom's outline are sufficient for us. Again, these are recommended, not required. Let's see. One other resource that I want to point to you guys, let's see. So basically, the primary textbook is more in depth with the concepts, while the supplemental handles problems. That's exactly right, Nikhil. The primary textbook will have all the theory, but it will also have problems at the end of each chapter. However, Shom's outline has solved problems. So you guys can you can take advantage of Shom's outline for a lot of practice. And signals and systems has been around for many years, right? This course has been taught both in online and in-person format. And if you go online, you will find a lot of problems to practice if you needed them. Now, I also want to point out one important resource for the class. So let me just show you guys where to find it. If you go on Piazza for the class, I'm just logging into Piazza for the class, for our class. And if you go under resources, if you scroll all the way down, you will find general resources on our Piazza page. And within the general resources, I have uploaded a detailed syllabus, and I've also provided a link to supplemental videos. That's what I want to point out right now. If you click on the supplemental videos, these are supplemental videos that were created many years ago by professors that have retired now. Professor Mike Wozni and Professor Alan DeRocher, they taught signals and systems at RPI for many, many years. And Dr. Jonathan Ashdown, he has very good Matlab tutorials. So I organized these. If I click on topic 1, it'll take you to a page where I've put many videos by each topic. So you can use a web browser to open these and watch at your convenience for the topic that you are interested in, right? So as we are going over signal classification, odd and even components of a signal, for example, try to go and watch, right? Some videos are short, some videos are long. They are not of excellent quality, but it's a very good resource to have so that you can refer and learn from very experienced professors who have taught the course at our university for many, many, many years. So you can get another perspective on the similar content. There's a video on review of complex numbers under topic 1. So if you are, I suppose everybody over here has understanding of complex numbers, right? How do you represent complex numbers? How do you go from Cartesian to polar coordinate system, Cartesian representation of polar numbers, complex numbers to polar form? How do you do addition, multiplication, division of complex numbers? What is a complex conjugate? So all of these ideas, if you are comfortable with that, that's good. I suppose you have some background on that, but if you are new to complex numbers, review that video under topic 1, and I've also attached notes for complex numbers written by Professor Tajer over here for you to quickly review complex numbers. And I've also pulled it up over here to show you guys. So this is Signals and Systems Complex Numbers by Professor Tajer, and it talks about the general ideas in a complex number system. How do you represent complex numbers? How do you go from one form to the other? How do you calculate the magnitude and phase of a complex number, and so on. So not too many things, maybe about 5 pages or so, 6 pages, that's it, with some examples at the very end. These should help you with homework number 1. So homework number 1 is essentially a review on complex numbers, and take a look at this resource to work on that. If you are very well versed in complex numbers, you won't need it, but just in case you need it, you have this particular resource. Nikhil asked a question, will we get access to all the back exams before exams? Yes, you will. More than you can imagine. I think I have back exams dating back 2005 maybe. So you will have a lot of back exams. I don't have all the exams from 2005, but I have plenty. So you will have access to them. Let's see. So I talked about complex numbers and how it is related to the homework, and where you can find that information. And I have also shown you the supplemental videos location. I cannot stress this enough. The supplemental videos, if you are new to Matlab, if you are, you are of course taking the class with me, you are going through the lectures, it is not required. But if you want to take a look at how other professors deal with the signals and systems, get their view on it, or maybe there is a certain topic that you feel a little bit weak on, you can go there and review it, and that will be an excellent resource. That is an excellent resource. So I spent quite a lot of time getting these videos from the retired professors and organizing them into like a web page. Okay, let's move on. Where were we? We talked about the textbook and all these things. Okay. Did we leave out anything here? No. Let's move on. Exam schedule. So we have 3 exams over the course of the semester. Exam 1 is going to be scheduled for Monday, June 21st. Exam 2 on Monday, July 26th. And the final exam is going to be on the last day of the summer semester, which is for us Thursday, August 19th. So those are the 3 exams. Exams are going to be proctored using Webex meetings. I will talk all the details about how the proctoring is going to happen close to the exam time. There are going to be 2 time slots for exams. One is going to be during class time from 10:30 to 12:30 p.m. on those 3 exam days. And then there is another alternate time slot from 8 to 10 p.m. So I'll ask you guys to sign up for the time slots as we get closer to the exam, and then based on that we can have those 2 separate exams. These will be 2 different versions of exam 1, exam 2, and final exam. Let's see. Questions here? All right. So bookmark. So put a note for yourself. Mark these on your calendar. Put a reminder for yourself so that we don't miss. Our exams are required, and I hope you don't miss it. Now, if you have extra time accommodations, please let me know ahead of time. Send me an email with your DSS note so that I can include that information to have the appropriate logistics for you. All right, let us move on. Homework and Matlab exercises. So one way, so homework is going to be, standard, right? I'll give you guys a set of problems. You will work on them on a piece of paper. You will scan them and upload them to Gradescope. And if you have any questions, you will go to the TA help sessions to get some clarification. So that's how homeworks are going to be. Some homeworks are going to include Matlab exercises. If you are new to Matlab, I would highly recommend you to use Matlab, not just to use them for homework, but also as a software that you have command over, right? So it is an excellent addition to your resume. If you know Matlab, that is going to serve you well come interview time. So this is a free software for you guys. If you can go to RPI software, look for RPI software, look for Matlab. Colin. All right. All right. Is there anything greater than R? All right, so we have got R, NumPy, and Matlab. By hand, Colin, oh my God, Desmos. So here, I dare you guys this. When there is an interview or when you are going to a career fair, for example, tell the employers that I learned how to do it in R or Desmos or NumPy, versus tell them I have full command over Matlab, and look at their response. So there's a particular reason why I really like calculator.com. So there is a reason why Matlab is the calculator on steroids that it has become, because it has such a strong toolbox for each of the fields that we as electrical engineers or computer systems engineers are going to need. So it has served me very well over the years, and I'm going to recommend you guys to use Matlab and get familiarized with it as much as possible. Okay, let's move on. So there are many versions, right? So sure. Here, in terms of software, nobody can convince me that something is greater than Matlab. It's just my opinion, mainly because of how important it has been throughout my grad school. Mainly in grad school, it has served me very well. So I can talk about how exactly it has made a big impact on my life. But for now, know that it has served me very well, and if you guys use it, you will see the real strength of that software. Mathematica. Okay. All right. So let's see. Assign. Oh, by the way, RPI software. It's a free software for you guys, right? So you can go to RPI software, log in with your credentials, and download Matlab. Every year, Matlab comes with 2 editions. There is a 2021A right now that is available. Later in the year, there will be a 2021B. So for now, you really can get 2021A or 2020B or 2020A. If you have installed it a few years ago, you can still use that, right? So there's not a problem for at least the things that we are going to do. If you have a version in the last few years, you can still use that. But the one that is current, the most up-to-date version is 2021A. So if you are installing Matlab for the first time, that's what I would recommend. And you will you will need your RPI credentials to get the copy. All right. So for assignment submissions and grading, we are going to be using Gradescope. The TAs are going to grade it on Gradescope. You guys will be submitting it on Gradescope, and we are going to try to return your graded work within a week. And as usual, as I do for my other classes, I will be providing the solutions, and you will have the solutions, and you will have your graded work. You can take a look at it, and if you see any sort of discrepancy, you can do some regrade requests for homework. But the time for that is 2 days after the graded work has been given back. But we are going to try our best to return the graded work within a week. Assignments are going to be assigned every class, but they are going to be due 1 week. For example, homework 2 will be assigned on Thursday, May 27th, but it will be due the following Thursday at 11:59 p.m. the following Thursday. Late assignments are not going to be accepted. So make sure that you submit the homework on time, 11:59 p.m. Eastern time. Don't wait until the last minute, you guys. I will drop 3 lowest homework grade scores. This is to accommodate for sickness, interviews, emergencies, for personal problems, and so on. You don't have to provide an official excuse for the 3 lowest scores. So you can use them wisely. I don't recommend you to miss any homework on purpose. But if there is, if you're not feeling well, or if you have an interview and you have to miss a homework, you know that the 3 lowest homework grades are going to be dropped. Questions about homework, and Matlab exercises. Going once, going twice. So, okay. The regrade policy is slightly different for homework and exam. For homework, you will have 2 days after you get back your graded work. You will have the opportunity to appeal for a regrade on grade scope within 2 days after receiving your graded work. But for exams, you will have a longer time within 1 week after the exam. But for this, you would have to explain me your request in detail using email. So email request directly to me within 1 week for exam regrades. And while you're doing any regrade request, take a look at the solutions first, look at all the details, and then try to appeal for it, right? There is a particular rubric that we try to follow for having consistency throughout the class. So it is applicable at some places, it may not be applicable. Regrade might not be applicable at other places. All right, academic integrity, which is a very, very important thing to consider for all of us, right? And if you go and look at the syllabus document, you can read all of the details about this policy. In general, it is going to be that any violation of any copying or plagiarism that happens and that is sort of noticed by the TAs or by me, if it is on a homework, it is going to result in a 0 score for that particular evaluation for the first time. If it is repeated, then it is going to result in a failing grade for the class. If it happens on an exam, we don't have any sort of tolerance policy for the exam just because the exams are of a higher weightage. So 0 tolerance policy for academic integrity as far as the exams are concerned. It will result in failing the class as well as it will go on your academic record at RPI. So take this very, very seriously. Grading criteria. For homework assignments, it's going to be 20% of your grade. For exam 1 and 2, you have 25% each. And then for the final exam, you have 30% of your grade writing on the final exam. So that's how this the grading for this class is spread out. Again, all these slides are uploaded on Piazza, so you don't have to take these down right now. You can look at this PDF later on after the class as well. And for those of you who are taking a class with me for the first time, I usually post slides on Piazza before the class, and after I write on them, I post after class slides as well. And you can do the same if you have, something that you can write on a digital device, or maybe an iPad. Then you can do the same. You can download that PDF, write on it along with me, and then you will have those notes. Okay, let us move on and start talking about signals and systems. So the first thing that we'll talk about is a car. We are just giving an example here to look at what is a signal. Our system is a car here, right? So our system right now is the car. And we are trying to monitor the speed of the car, which is sort of an outcome or an output, right? So speed is the output signal or the outcome or the response when the driver is applying more gas or less, right? So this is your input. So as you apply more gas, the car is going to speed up. Now, there is no feedback in this, right? So you have an input, goes to the car, and the result of that is an output signal. And if you monitor the speed of the car with respect to time, you will see that increasing as you increase the gas that you're applying to it. So in this context, you have an input signal on the way to the left, amount of gas, And then you have all the way on your right, you have the speed of the car, which is the output signal. And both of these are for the system, which is the car in this particular example. Now we can do some interesting thing with this, which is to add a feedback system, right? So feedback over here, who is controlling the feedback? Well, you are controlling the feedback. Using what? Your sensors. What are your sensors? Your eyes, right? So as you are increasing the amount of gas, as you are pushing that pedal down, you are visually looking at the speed of the car, and then you are using that information to in the feedback. So the feedback system is you sitting in the car monitoring whether the speed is too much or too small, right? So if the speed is too much, then you would apply brakes. And if the speed is too little, then you are applying more gas, right? So you are able to maintain or control the speed of the car with the car and the sensors that you have, that you are in the feedback, right? Now, let's take a slightly different example. If you think about these three things, system, input, and output, you can really apply this to a lot of real world situations. And as we go through this course, I encourage you guys to think in that manner. I want you guys to take inputs and output signals in the systems and try to apply that to real world scenarios. Because this particular course, Signals and Systems, I may have mentioned it to many of you in the past. In my opinion, it is the best course as an engineer you can take during your 4-year undergraduate degree. Period. I enjoy teaching it even today. And the reason for that is because of how elegant the solutions to certain problems can be. Every time I teach this class, I look at it slightly differently, and I enjoy it because of that, right? So there can be some very brute force, sort of long mathematical proofs, but they can be very elegant and smart ways of solving the same problem, which sort of brings that attractiveness as far as I am concerned. Now, let's think about something else. I'm going to add a slide here and show you guys that you can really think about signals and systems in various other aspects. So let's say we have a room here, and the room I'll take is low 4050. This is going to be the classroom we are going to be in, right, starting Thursday. So suppose we were in this room and I'm making this my system. Right? And then I'm going to be there in front of the class delivering a lecture. So my voice is going to be sort of the input to this system. So my voice is going to be an input to this system. And let us suppose that what you hear is the output of that system, right? So I'm talking about strictly in the sense of voice, right? Sound signals. So I made my voice as an input to this particular room, and what you hear is going to be your output signal, right? So here you have this excitation or input, and on the way to the right you have the response of the room. So you've got your voice as the input system and what you hear as the response. I've just put low 4050 over here because maybe you can think about a real room, but there is also a system right now between you and me, right? And it starts with my microphone and the network, the Webex meeting, your speaker to you, right? So my voice to your ears, there is a system between us. We also have it right now. But I want you to picture the actual room. Now, is my voice going to be exactly equal to what you hear? That's a question I'm posing to you guys. So my voice, let us say I'm going to call this M of T. M for my voice, T meaning it is going to be a function of time. Let us say I'm monitoring the amplitude of my voice, the strength of my voice as a function of time. And what you hear, is it going to be equal to, no, your voice sounds different in your head. Right, recording hardware isn't perfect, okay. So pulse compression, all right. So it's, in general, you're saying what you hear is not going to be M of T. So I'm going to say this is going to be M hat of C, for example, right? There's a volume gain, there it is, yeah. So acoustics in the room, nice. So there is going to be a reduction or attenuation of my voice, right? So the farther you are from me in the room, the lower volume that you are going to hear. So that's going to affect the amplitude of M hat of T. And again, as Lindsay pointed out, there are going to be acoustics of the room. The characteristics of my system are going to change M of T. Maybe they will add some echo to my voice. Maybe they will definitely disperse my voice. And depending on where you are in the room, it will affect the strength of the signal, the amplitude of the signal, right? So clearly, M of T is my voice, M hat of T, it's not going to be equal. It is going to change. So let me pose a question to you guys. If I were able to write M of T in a mathematical fashion, and if I were to characterize my system in a mathematical fashion, as engineers, do you think it should be possible for you to know what M hat of T is? Yes. Yes, in theory, yes. In theory, of course. So if I mathematically characterize my input, and if I mathematically characterize my system, then theoretically, I should be able to find out, without actually hearing what you hear, without actually measuring what you measure, what you hear, I should be able to mathematically characterize even M hat of T. Now let me pose a different question. If I tell you what M of T is, and if I tell you what M hat of T is, can you maybe comment about the system characteristics? Sure, yes. So if I tell you what the input is, and if I tell you what the output is, then I can also talk about the system characteristics. It is going to be about characterizing the system. Now there are certain things that we have to be careful about. What is that? One, the system cannot change over time, right? So it has to be a time invariant system, time invariant. Because if it's a time varying system, then it is going to give one response at one time, another response at another time. So we are going to require our system to be time invariant. At least in terms of an assumption, we should be able to make that. And also, our system should be linear, which sort of means this way, right? If I was saying at one time my strength of the voice, the amplitude, then you hear 1 times the output. And if I increase my volume by a factor of 2, then what you hear should also increase by a factor of 2. And it should keep going on in that linear way. So the system should be linear, and it has to be time invariant. If it is linear and it is time invariant, then you tell me the input and you tell me these characteristics about the system, and I can tell you what the output is going to be. I can predict the output. I can estimate the output. without actually having to hear what you hear. I should be able to tell you, right? So you can do all of these cool experiments with signals and systems, provided it is a LTI system, linear and time invariant. Now, let me take another example here. I took the concept of voice and what you hear in the room, right? Let us take this stone thrown into a pond. What is the output? A ripple, right? So ripples. Oh, I was not talking about that kind of throw, but I'm just trying to drop a stone into a pond, right? Like it's going to create some ripples. So if I throw a stone into a pond, and if I was able to characterize the pond, the characteristics of the pond, I'm characterizing it, then I can tell you how the ripples are going to be. And also, if I was able to do that, then if you say throw 4 stones, I should be able to predict how the ripples are going to be as a function of time and position, right? So you can do all of these. So you can think about these ideas, and we will know more details about how do you characterize a linear time invariant system and so on as we go through the lectures. But I want you guys to start thinking about signals that are real and associate them with the kind of the concepts that you learn in class. You should try to start thinking about signals that are real, right? Biological signals like your heartbeat or your body temperature also can be really good signals for you guys to start thinking about in terms of these ideas. Let's see. All right, enough of that. Let's move on. So the objective of this course is to do that, is to understand the fundamentals of analyzing and designing such systems. Can you, a car to move at a constant speed, can you design systems such that your speed is constant? Maybe you use some feedback. Maybe you use yourself, your eyes, as the sensors, or maybe you have cameras to give you that signal in an electronic way, and then you can control the speed of the car. Or room temperature to remain constant using feedback, or for an airplane or a drone to monitor the altitude and to fly level, right? So how do you design systems for that? What kind of feedback would you need? How would you characterize the system? Because there are two systems now, right? One is the airplane and the other is the feedback. So the whole goal is to talk about signals, input and output, the system, and also the feedback system. Feedback system is going to be added on to our list later on in the course. All right. So here it is, signal plus system. You've got your input signal or excitation way on the left. You've got your system here. You've got your feedback system here, which is essentially providing some sort of control over your output signal or frequency or response. Now, another thing that you can think about when you think about a system with feedback is if you have seen sort of a public audience, right? So suppose there is a mic and there are some speakers in an auditorium. What could happen? Well, because you have an active mic and you have speakers in the same room, there could be feedback, right? And what happens because of that? Most of you may know this. You will have that very uncomfortable loud sound, right? Why is that? Because the reason why it happens is because the gain of your mic is too big. So if your gain of your mic is too big, you have a positive feedback. And when you have a positive feedback going back into your system, it is making your input signal larger. Consequently, it is shooting your response, leading to that very uncomfortable noise. So what can you do? You can reduce your gain of your mic, or reduce your gain of your feedback system. If you do that, then you will be able to control that and then sort of have a balance between what you are saying and what is projected using the speakers. All right. That's an example of unintentional feedback. So what's a signal? We've been talking about signal. What is a signal? It is a sequence of values in time. We generally talk about amplitude versus time, but we could also talk about some other parameters of a signal with respect to time. So when you think about a signal, you're thinking about a time axis. Let me draw it over here. A time axis. So this is your time. And you're thinking about, say, f of t, right? Some function of time. Generally, say, an amplitude, right? So amplitude of my voice, for example. So let's see, I'm going to just simply draw some arbitrary signal. In red, I've drawn some arbitrary signal. It shows me how f of t is changing with respect to time. So that's a signal. It could have mathematical properties, right? You could express f of t in closed form, but real signals, that is quite a challenge to express f of t in mathematical form, right? So say real signals such as your heartbeat or your body temperature, for example, it is going to be difficult for you to express that, something that's arbitrary, in a mathematical closed form. So what can you do in that case? Well, you can break it up into pieces, right? So you can say, all right, let me break it up into very, very small pieces and then express it mathematically. Maybe from here to here. And then from here to here, and then from here to here. So some sort of approximation, and then you can maybe express that in a mathematical form. So generally, when you have real signals, it is not possible for you to represent the entire signal in a mathematical closed form. But what you can do is you can talk about its characteristics. So you can talk about, oh yeah, this signal is occupying a bandwidth between 10 hertz and 100 hertz. And it has a low amplitude in low frequencies and it has a higher amplitude in higher frequencies. So you can talk about the characteristics of a signal even if you are not able to write the signal in closed form mathematically. So we'll learn how do you do that as we go through the lectures. So some examples: an individual's heartbeat, an individual's voice, body temperature with respect to time. All of these are examples of a signal. Light intensity in a room, for example, over time. Another example of a signal. Force applied on an object. Another example of a signal. Output voltage of a circuit. That's an output signal. Input current of a circuit. That's an input signal, right? So voltages and currents, we are used to seeing voltages and currents as signals. We have done that many times, but now I want to also ask you guys to think about it in terms of real signals. Nyquist Shannon coming up soon, I can feel it. Yes, we will be there in a lot of detail later on, but we'll touch on it now. All right, so for time, what happens is this. You will usually need a lot of variables to talk about time. So time generally, if you only had one, sure, you can use t for that, right? No problem. However, you will have multiple time variables, especially when we start talking about convolution. Then you will have two for sure. So what do you do when you need more than one time variable? Well, you can use t, you can use tau, you can use t prime, and generally for fixed times, say at t1, at t2, at t3, you can use a subscript. So all of these can be used for continuous time. This is not for discrete time, that's for continuous time. So we are talking about f of t. It's a continuous time signal that we are talking about right now. F, in our example, refers to the whole signal. F of t is your whole signal as a function of time. So f of t refers to the value of the signal at any given time, t. So if I go back here, I can say, all right, what is t1? Maybe t1 is over here. What is t2? Maybe t2 is over here, right? So if t1 is over here and t2 is over here, then I can project these values onto the y-axis, on the vertical axis, to find what that value is going to be. Well, obviously, I'm going to get what? Over here, I'm going to get f of t2. Function evaluated at t2. And over here, I'm going to get what? F of t1. These are continuous in time, and they're also continuous in amplitude. Right? So every time, you will be able to know what that value is going to be. All right, so that's your signal. Let me talk about some common signals. And we are going to keep adding to this list as we go through. One over here is a constant signal. Nothing fancy happening here, it's just a constant signal. So how do you represent a constant signal? Let me sketch it. Well, the axes I will draw in black. All right, that's fine. I've got t here as a function of time. And then for the y-axis, because I'm doing 4 of them, I will write f1 of t here. This is my first signal. This is a constant signal. So in red, maybe I can draw the signal itself. Constant. Okay. And it is continuing on the right as well as left. Say this is time 0. And let us pick some amplitude. Let us say m. So f1 of t equals m for all time. That's a constant signal. Nothing interesting, but I'm also going to write the bracket notation. Bracket notation, also called as piecewise notation for the signals. So for the bracket notation, what do I have? f1 of t equals m independent of time for all t. Right. So there's no bracket here. There is just one value m. So that's your constant signal. What is the frequency of this signal? Zero. No frequency at all. Zero. Excellent. So the frequency of the DC signal is 0. So when you start talking about time to frequency conversion using a Fourier transform, you will see that there is only one line in the Fourier transform of f1 of t, which is going to be at frequency equals 0. Right? There is not going to be any other frequency for this particular constant signal. All right, let's talk about unit step. You're going to see unit step, in short, u of t, a lot, especially during the, well, all throughout the course really. Let's see. And that would also be used for any DC offset. That's right, Bennett. That's right. That's exactly right. So suppose you had a sine wave, right? A sinusoid, if you had a sinusoid of frequency 100 hertz that had a DC offset, then you will see two things in the Fourier transform of that. One is a tone at 100 hertz, and also because of that DC offset, you will also see something at frequency 0. All right, let's talk about unit step. So how does the unit step look like? I have this. Again, I'm going to use time here, and I'm going to use f2 of t here, which is really my u of t. A unit step is indicated by u of t. And it simply is this. It is going to be 0 for time less than 0. Maybe I should increase this a little bit. Maybe make it 0.7. Sure. It is going to be 0 for time less than 0. And then at time 0, there is a jump or a step. And it is a unit step, so it is going to be from 0 to 1. So this value is going to be 1, 0, that's it. And it is going to continue that same way, right? So this goes this way and this goes this way. That's your unit step. How can you express it in the bracket notation? Well, now you have got two pieces, right? Bracket notation or the piecewise notation. f2 of t is going to equal either 0 or a 1. It is going to be 0 when time is less than 0, and at t is greater than or equal to 0, it is going to be 1. Now, I would like to point out this. At time 0, actually there is a discontinuity in the signal. It is jumping instantly from 0 to 1, right? So later on, when we try to zoom in and observe this jump in more detail, we will actually evaluate this as a rectangle whose width is tending towards 0, right? So it's not really greater than or equal to 0. It is greater than 0, but right now we are assuming that at 0 it is already reached 1. Later on, we are actually going to evaluate this as a limit. Maybe we'll start off with a rectangle here, and then we will try to evaluate the width of that rectangle as it tends to 0. We are going to use that to define the unit step. All right, let's see. So that's your f2 of t. What is the question? What does v with the right? Okay. Let's see. Okay, we have got unit step here. Next, we go to a rectangular pulse. All right, so let's do a rectangular pulse. No problem there. You've got a time there. We are calling this f3 of t. And I will use some rectangle. Can be 0 here. Come on. And then it can have a pulse here and then go to 0. And some height, maybe n, and then this is 0, this is say t1, and this is say t2, right? And then it is continuing over here as 0, and then over here as 0 as well. Right. So that's a rectangular pulse of height n between t1 and t2. So how do you express this? Well, again, bracket notation. What I can really do here is I can say it is n between t1 and t2. And then it is 0 otherwise. Right. So actually, let me remove this over here. T1 less than T. Okay, that's fine. So that's your bracket notation for F3 of T. Next, a sinusoid. So a sinusoid, fine, we can draw an example. It's going to be a periodic signal. How does it look like? Again, your some sinusoid, right? it's a periodic signal, and it is going to have 4 parameters: amplitude, what is that, frequency, what is that, offset, and one more, phase. Right. So 4 parameters for that sinusoid. It's a periodic signal. So you can also express that in bracket notation. F4 of t is cosine 200 pi t, for example. All right, questions about common signals, the ones that we have seen so far. How do you express them graphically? How do you express them in a bracket notation? All right. Now, as far as real signals are concerned, is there a discontinuity on the... Yeah, there are 2 discontinuities. One is over here, and then one is over here, right? So again, we will try to evaluate every discontinuity by using that kind of a limit, right? So at t1, I'm assuming that it has already reached n, and at t2, I'm already assuming that it has reached 0. There are 2 discontinuities in F3 of t. All right, let's see. Real signals. So, like I mentioned, for real signals, it's cannot be really described mathematically in closed form. However, its characteristics can be captured mathematically. Then that's what we are going to try to do. Real signals example: FM radio signal, biological signals like your heartbeat and body temperature, like we talked about, cable TV signal, Ethernet signal, your cell phone signal that your cell phone is receiving all the time. So all of these things are real signals. But our goal will be characterizing properties of signals mathematically. That will be our focus. Now let's start with signal classification. And there are a lot of ways to classify signals: continuous versus discrete, analog versus digital, real versus complex valued, energy versus power signals. So there are different ways of classifying signals. This could be input or output signals. It could be either one of them. So let's talk about the first classification, which is continuous versus discrete. So on the left, we have a plot of a continuous signal. I'm monitoring some amplitude of a signal with respect to time. Time axis is in milliseconds. The amplitude is whatever the amplitude. If it's say a voltage waveform, then the amplitude is voltage. And if it's a current waveform, it is current. If it's a force, then it is in newtons. Whatever that is, right? Some amplitude. It's a continuous signal, and it's not periodic. It is sort of sinusoidal, but it's increasing in amplitude as the time increases. What is it? So signals take values at any given time, and as you can see, if you pick any time over here, you will be able to find out what that value of that signal is going to be. For example, if I say 10, you will be able to say, yeah, maybe about 2.25. 15.1, yeah, you will be able to tell me. 30.5, you will be able to tell me. Any time I mention in milliseconds, you will be able to tell me what that amplitude value is going to be. So in terms of time and amplitude, it is continuous. The plot is continuous. Every value is being recorded, stored, processed. That's what is happening over here for continuous. Signals take values at any time t. Now if I move to discrete, what do you have? Signals take values at discrete values of time. So they are able to still take any value really, but they are able to take values only at discrete times. So one over here at 0, one over here at maybe 1 second, 2, 3, 4, 5, 6, 7. So every 1 millisecond, there is a value that is being taken. So it has become a discrete in time. So what did we do here? How did we go from a continuous signal to a discrete signal? How did we go here? Sampling. There you go. All right. So if you do sampling, you go from continuous to discrete. Quantizing happens for later on, right? Quantizing involves you to become discrete even in the amplitude. You see, now in terms of amplitude, the signal can take any value really, right? So when you're quantizing, that's no longer the case. You're also snapping to the closest level as when you're quantizing. So right now we are only doing sampling. Essentially means I am picking out values of the signal at discrete times. So why is this useful? Well, you can take a continuous signal. Your real signals are going to be continuous. You can sample it. You get a discrete signal. And once you get a discrete signal, you can store and process discrete values of the signal as opposed to continuous. Because you are going to have fixed amount of much smaller amount of values that you need to store, you need to process, all of that. You are going to have a lot less to worry about. So the next question is, did we lose information while we were doing sampling? How can you really find that out? Well, you can find that out really by trying to reconstruct the signal from the set of samples. So to go the other way. So that's called reconstruction. So maybe while you are doing reconstruction, you may be able to get this, or you may be able to get somewhere close to this, right? But clearly, by looking at these two, you know that if you do not have enough samples, then you will not be able to reconstruct the signal. If you have enough number of samples or more than enough number of samples, you will be able to reconstruct it. So right now, how many samples do you have? Well, it looks like you have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 samples in one period. If I was thinking about it as a periodic way, it's not a periodic signal, but if I was assuming that it was periodic, you kind of have 10 samples in one cycle. You only need 2 samples per cycle to be able to guarantee reconstruction. It also depends upon where those 2 values are. Yes, so that's Nyquist rate. Nyquist rate is sample the signal at least twice the maximum frequency in the signal to guarantee that you will be able to reconstruct it. Right now we have 10 samples in one cycle. We have plenty to be able to reconstruct it. So you will be able to save memory space, you will be able to save the processing power without losing any information. So that's sort of the power of sampling and reconstruction. We have dedicated lectures for these. We have several techniques for sampling. We have several techniques for reconstruction. Very interesting topic later on in the course. But that's what is happening over there. All right. So a couple of things about discrete signal. You have some granularity in time, right? So you are taking the sample every 1 millisecond. So you have granularity in time. However, in terms of amplitude, you are allowing any sample to take any value, really, right? So this guy is taking 2, this guy is taking maybe 1.75 and whatever, right? So in terms of amplitude, it can take any value in amplitude in the y-axis. We have only limited it in terms of the x-axis. We have made it granular in terms of our x-axis here for the discrete signal. All right. Next one is the second classification, which is analog versus digital. All right, so we have an analog signal, which essentially means signal can take any amplitude value. The blue line is the analog signal. It can take any value in time. Amplitude, right? Any value in amplitude it is able to take. However, a digital signal can only take discrete amplitude values. So you see over here, the difference was this can take only discrete values in time for discrete signal. Over here for digital signal, it can take discrete values in amplitude in the y-axis. So the blue line is the analog, and when you digitize it, it looks like a staircase signal in red. So what happened? What did we do? We did a analog to digital conversion, ADC. That's what we did. How did we do it? Well, the first thing that we had to do is look at the dynamic range of the signal. What is the dynamic range? Dynamic range means in the given amount of time that we are observing the signal, what is the highest and what is the lowest point, right? How is it, what is the range of that signal? So from what it looks like, it seems that between the 0 and 20 millisecond mark, we have 2.5 as the highest and maybe 2 as the lowest, right? So 2.5 plus 2.5 to -2, that's sort of your dynamic range of this analog signal. What you do is, next you try to come up with a discrete number of levels to split that dynamic range. So let us suppose that we have a 8 level uniform quantizer. What do you do then? Then you say, all right, I've got that as your let's see, that's your highest and that's your lowest. You're going to split it up into 8 levels equally because we are doing uniform. That's 1, that's 2, 3, so I've literally chopped it into 8 levels, and with each level, you see the amplitude is discrete, right? The amplitude is snapping to the closest level. So for example, over here, all these points are closer to this level. So they are all snapping to that. All these points, we are trying to snap to the next level here. So it snaps to that, snaps to that, snaps to that, snaps to that, and so on. So what you can do with this is actually get a bit sequence that you can use for digital communication. What you can do is you can associate 0, 0, 0 with this, 0, 0, 1 with this, 0, 1, 0 with this, and so on, right? So after you quantize, with each quantization level, right now we have done a uniform quantization, which means that we have spread out all those levels equally. Doesn't need to be equal. You can have a non-uniform quantizer as well. But once you do that, once you have your 8-level quantizer, you can associate bit values with this, and then you can communicate the signal as this, right? So the first thing that you're sending is that 0, 0, 1, then 0, 1, 0, and so on. This, of course, is arbitrary. You can switch this around. It depends on the person who is designing the system. But that's how your communication can work. Take an analog signal, go through an ADC with a specific number of levels in the quantizer, and then associate bit values for each level. Then you transmit that particular bit sequence. That's in the context of digital communication. All right. So again, to summarize this slide, the main point was what? In an analog signal, you have any amplitude value that the signal can take. For digital, it's going to be discrete amplitude values. So the signal can only take this one, or this one, or this one, or this one, any one of the levels for the quantizer. All right. Next way to classify signals is to look at whether it is periodic or aperiodic. So a periodic signal has to simply satisfy this particular criteria. f of t plus cap t equals f of t, where t, cap t, is used as the time period of the signal. So it is also called as a t periodic signal, right? So some textbooks call it t periodic. What does that mean? T periodic essentially means it's a periodic signal with the time period t. But for that, this condition has to be satisfied. So on the left over here, we have a periodic signal. It's a cosine. So let's see. What is the signal over here? How can I write it mathematically? The amplitude is what? 2. It's a cosine. And it is 2 pi. What is the frequency? Well, the time period is 10 milliseconds. If the time period is 10 milliseconds, the frequency is going to be 1 over t, which is going to be what? 100 hertz. So that means that this is going to be 2 pi times 100 t. Let me just write it as 200 pi t. Right, so that's the signal there, 200 pi t. So the question is, if I'm calling this periodic, then it has to satisfy that condition, right? It has to satisfy this condition. Is it? Let's find out. So let's take cap t or f of t. Let's take t to be 2 milliseconds, right? I'm just taking t to be 2 milliseconds. So where is it? Let's see, 2 milliseconds right here. And if I add 10 milliseconds to it, I get 12. All right, 12. Exactly the same value, right? You could have picked any other time value as well, 3, 4, anyone really. So that's your periodic signal. If it satisfies that criteria, then you know that it is a periodic signal. But if it doesn't, then it's an aperiodic signal. So an aperiodic signal is shown on the right. There's no such cap t that satisfies that criteria for this. So it's an aperiodic signal on the right. Questions about this classification, periodic versus aperiodic? All right, let's move on. We'll try to do another classification here. This one is causal versus non-causal signals. Not systems, for signals. So a causal signal is if f of t equals 0 for all time less than 0. That's a causal signal. So I can just maybe for all of these things, I can anti-causal and non-causal. So for the first one, I have a causal signal which is supposed to be 0 for all time less than 0. Right, let's sketch this. This can be arbitrary, right? So it can be anything really. So I'll say 0 and then some signal there. That's a causal signal. An anti-causal signal is f of t should be 0 for time greater than 0. Sort of the opposite. That's an anti-causal signal. Oh, by the way, I need to not forget zeros because zeros are very important here. And also This is say f1 of t, this is say f2 of t, this is say f3 of t. A non-causal signal is neither causal nor anti-causal. So how should I draw a non-causal signal? Cannot be this or cannot be that. So that's going to be something like this. Say you have this and you have this. That's going to be your non-causal signal. So causal, anti-causal, non-causal, right? So I've just picked up some arbitrary shapes for my signals, but just to show that these are some examples that satisfy these criteria. Questions about this classification: causal versus non-causal versus anti-causal. These are for signals. Won't this need to be changed on how you define the function? What do you mean? Won't this change based on how you define the function? So yeah, exactly. So once you have defined the function, then you can comment about whether the function is, whether the signal is causal or anti-causal or non-causal. If it is 0, is it causal or anti-causal? If it is 0 all the time, then I would classify that as a causal signal. If it is aperiodic, that goes from 1. Let's see, if it is aperiodic, that goes to 1 at 0. So 0 is not included in the limit here, right? Spikes at, you're talking about an impulse, right? An impulse is a non-causal signal. Because an impulse, which is something like this, we are going to evaluate that as a rectangle whose width is going down. All right, let's see. So I said a 0 signal would be causal just because causal is sort of a good news, right? So it is, it could later become, so if it is 0, right? And if you are monitoring it after time, then it has a possibility to become something non-zero later. So I'm talking about it in the sense that in the past it has already satisfied, in the future it could break. All right, let's see. Okay, I think we are at the end of time for this class. So what we can do is we can pick it up with the size of a signal to compute energy and power of signals on Thursday when we meet in person. Note, homework 1 has been assigned. It is due Wednesday of next week. It has to do with review of complex numbers and complex conjugates and conversion between Cartesian and polar. So review the document that is uploaded on Piazza, and then you should be able to complete. Monday is a holiday, Satya. So our next class is Thursday, May 27th. After that, we meet on Wednesday, June 1st, I think. No problem. All right, so we'll pick it up with the size of a signal, and we'll talk about unit step and odd and even signals, a ramp function, all of those things on Thursday when we meet in person. Thank you guys. Have a good rest of your day. Okay, so Piro needs to be added. Go ahead. I do. Yeah. So on Piazza, there are two sections, right? There is a lecture slides before. Let me show you. If you go in Piazza, you see this lecture notes, right? Yes. No problem. Yeah. Oh, is it your first of the year? Yeah, I know. We have only met online. Yes. Okay, Dan also needs it. All right. So here, let me know, you guys. So there was Piru needed it. Dan needs it. Who else needs to go on there? I think there's like only two people have told me. And for just an excuse to go to the tech dump. Oh my, Colin. Oh my gosh. Ben, I need. Oh yes, Ben. So I have one class after the other. So you know, I'm gonna add you to that. It's on my to-do list already. I found a Mac Pro in. Oh really? Oh yes, I remember. Yes, I remember.